So let me share screen. Just give me a second. So is my voice audible to all of you? Hello. Okay.
Sir, your slide is working.
Okay. Thank you. Okay. So now, so far in this course that we have covered the deep learning. Okay. First one that is the AI. So in this, that already that we know before, just this FDP, this artificial neural network. So how to improve the performance of this ANN by this regularization, okay, dropout, early stopping. Then the second is that is CNN, that we have covered the CNN. So in this CNN, the family of CNN, uh, families of CNN that we have covered, Planet, AlexNet. Now the third is, so how to apply this deep learning on the sequential data. Okay, so for this one that we have covered RNN, and in the last lecture that we have covered this LSTM. Okay, so this is about the sequential data, and the fourth one is sequence to sequence model. So here in this one, that today that we will discuss encoder decoder architecture. Okay, then we will discuss here in this FDP the attention mechanism. Then we will discuss the transformer. Okay, fine tuning of transformer. And the fifth one is unsupervised is unsupervised learning using DL. Okay, so in this module that we will cover the GAN, generative adversarial network. Okay, then this autoencoder. Okay, so mainly this we will cover in this FDP. Okay, so the CNN that already that we have covered, this RNN, LSTM, this one, this already that we covered. Okay, so now today that we will discuss, we will see the this sequence to sequence model, encoder decoder, then attention mechanism, then transformer. Okay, so now autoencoder that we will see this topic, this module in a next other day. So first, this sequence to sequence model. The beginning of this sequence to sequence model that are started from this RNN. Okay, so RNN actually is specifically designed for the sequential data, that is language, that is or sentences, or the time series based data. Clear? So now there are three type of, that is RNN. There is three types of RNN. So first type is, that is many to one. So in this many to one means this one is the RNN. Okay. This one input here, so many to. So many to one, that here input has a some sequence. Here the input that has a some sequence, and output data. This one is the output that has no sequence. It is a simply a scalar. Okay. This one is a simply scalar or a number. Okay. So that we have that very good example just to understand this many to one. That is example is sentiment analysis. Here, so here the output, if suppose output is one, that is a positive sentiment. Okay, if output that is let's say zero or close to zero, that is negative sentiment. Okay, so that is this one is the first type of RNN. The second type is one to many. So here in this input is scalar. Here this input that is scalar. Okay, so not necessarily scalar, but one such input where there is no sequence. Okay, here no sequence, and the output is something like this is this in which there is a sequence. Okay, here is a sequential data. Okay, so the output is in the sequence. So here the example is image captioning. Okay, so the input is one single image, and output is the caption of an image. Suppose one person is playing, let's say, is cricket. So the caption that may be Sachin Tendulkar is playing a cricket. If you show one image to the model, then the output, then the caption of the image that may be the Sachin Tendulkar playing cricket. Okay, so means a sequential form. Now third is many to many, many to many. So many to many, this one is a kind of this many to many. So here the input that you give a data that has a sequence, and you will get the data output which is also in the sequence, that is in sequence. Okay, so here further this many to many, that is again the two kind of this many to many. If we divide this many to many on the basis of the input and output. Okay, so many to many synchronous, this one is many to many synchronous. Here both the input as well as output both have the sequential data. Okay, both have the sequential data and the number of words in a sentence that are same. But here the asynchronous many to many. So the reason is, the point is, due to the length of both input and output, the length that is not same. So here this side you can have the given input. Okay, let's say, and the output is a sequential that is more than 5 number of words, or maybe less than 5 number of words. Okay, so the example of this asynchronous is, that is machine translation. Okay, so language translation, that is a asynchronous many to many. So maybe some time that you may get the sequence of input and output are equal, but most of the time the number of words in a input sequence that may not be equal to the number of words in a output sequence, in output sentence. Okay, so the example is, that is machine translation. Here the example is machine translation. And second is, that is text summarization. Okay, text summarization. So basically that we have a very big text. Okay, let me write here above. This one is the text summarization. So if we have suppose very big text and you get a summary of it, suppose, so here input is sequential and output is also is sequential. Okay, that is a text summarization. Next example, that is question answering. This one is the second. Third is question answering system. Okay. Fourth, that is a chatbot. Fifth one is, that is a speech to text. Speech to text. That is a caption. Okay. So this one, these are the example of this asynchronous many to many array. Okay. So basically sequence to sequence model, here this sequence to sequence model seek to solve the asynchronous many to many problem. Okay. So now the first let us start the history of this sequence to sequence model. And in this one, the first model is encoder decoder. So first is the encoder decoder. So this solution is proposed in 2014, and this was the actually one of the first attempt to solve sequence to sequence problem like machine translation. So obviously there are some drawbacks. There is some flaw in this encoder decoder. So that is why the second solution is proposed that you may call as the attention mechanism. Attention mechanism. Okay. Now thereafter the transformer. Okay. Then transfer learning and the last one that is a LLM. That is a chat GPT. Okay. So this all this model that we will see in this FDP. So today that we will see the encoder decoder in detail. Okay. So the first stage is that is the encoder decoder. So encoder decoder architecture. Okay. So there is a one research paper here. The title of the research paper I am writing here, which was proposed in 2014, and the paper name title is Sequence to Sequence Learning with Neural Network. With neural network. Okay, maybe I will share this paper to you. So the first author name is Ilya Sutskever. He is the founder of the ChatGPT. Okay, so he is the first author of this article. So the researcher that proposed one different architecture to solve this sequence to sequence problem that are called as encoder decoder. This encoder decoder network. So in sequence to sequence, we have the input sequence. This one is the encoder. Okay, here the input sequence. Okay, and here the decoder, and we can create an output sequence from this decoder. This output sequence. Okay, so let us say we want to do something like machine translation, say English to Hindi. Okay, so the researcher they proposed very simple solution that our architecture that will have two parts. Okay, so one is this encoder and the second is decoder. So encoder will process the input sequence, okay, word by word. Process the input sequence word by word and compress all the information, okay, and compress all the information, okay. This compact representation of this sequence, okay, this compact representation of this sequence then we feed into this decoder. This one is the compressed representation or compact representation. Okay, and decoder will read this compressed information and solve it one by one, and it will produce the output sequence one by one. Clear? Okay. So now the question is, what is inside in this encoder and decoder? What is inside here in this encoder and decoder? So the answer is LSTM. Okay. So here in this encoder, in this LSTM is used. So we can use GRU or RNN. The LSTM is okay. But in this paper they work with LSTM. The researcher they work with LSTM. Okay. So now here we are sending one word here in every time step. Okay. Clear? So the internal state of LSTM. So here let's say this one is a encoder and this is a LSTM. One is the LSTM. So the input state is cell state and hidden state. Cell state and hidden state. Cell state that is CT, hidden state that is HT. So this cell state and hidden state are basically update all the time, and they are still as of now compiling all the this word in this sequence. Correct? So as soon you send the last word in this input sentence, when you send the last word, the final output that come out after this last word, you can understand this as a compressed representation of the entire sentence. And now you send this compressed representation to the decoder. And in decoder, the same step that same step that will be followed. There is another LSTM setup inside this decoder. So decoder that will do in a step-by-step manner to calculate this output, and the output that is again that is in sequential. Correct. And this compact or compressed representation that we call as a context vector. Context vector. Okay. So this is how encoder decoder that module works. So there's a one encoder decoder. There's an input sequence inside this encoder. LSTM setup is there. Here in the decoder again the LSTM setup is there. Okay. Now we process this input sequence word by word. Okay. Correct. Then whenever just we send the last word, okay, then this encoder summarize this whole word in a sentence in a form of this context vector, and this context vector that we will send to this decoder as an input, and decoder that again step by step it provide the output in a sequence manner. Okay, so now the drawback is here. So drawback of this encoder and decoder. So the point is now what happened in this encoder and decoder module. So this encoder and decoder module that is used to work well when you put it in a small sentence. When you give a small sentence, then it works very well. Okay, very fine. But as you give longer sentence and you are saying that the whole paragraph you translate from English to Hindi. Okay, here in the long paragraph, the output that will not good as it provide the output in small sentence. So when people try to understand the reason behind this, and this encoder is sending the information, summarizing the entire now in the form of the compressed representation entire information into a vector. Okay, that we call as a context vector. So what is happening is that in this whole process, when it summarizes the whole word in a sentence, okay, this input data, when you compress this information, the entire load is on this context vector. The entire load is on this context vector. Now problem is if the sentence that become too low, okay, if the sentence become too long, then initial word that this encoder decoder that start to forget. So basically the problem is short term memory. So the problem is short term memory. Okay. So that is why the decoding that has happening was incorrect. Decoding of this output sequence that was not correct. So the mechanism that was developed, which we call as the attention mechanism, that was the attention mechanism. Okay. So now this one is the kind of brief idea of this encoder and decoder. Now that we will see inside this encoder and decoder, the architecture of encoder and decoder, and what is happening inside in this encoder and decoder, and how it works with this LSTM. Okay, how we provide or give the input sequence word by word, and how do we get the sequence in the form of the output word by word, step by step. Okay, so up to so far, if you have any doubt, then please let me know. Is this point clear to all of you? Okay. So now the next, that is encoder decoder in detail. So the point is why this sequence to sequence data, okay, this one is difficult to handle. Okay. So now question is why the sequence to sequence type of data is is difficult to handle. So there are three challenges. So first challenge, our input is, since it is a sequence in some language, so obviously it has a variable length. The input that has a variable length. Okay. So you may not get the same all the time, same length of a sentence. So the sentence that can be of 2 words, a sentence that can be of 200 words. Okay. So the first problem, the first challenge is our input, was this input that is a sequential data, so that has a varying length. Okay, so input side that has a variable length. Now the second challenge is output, that is the output from the decoder. Okay, in our encoder series. Okay, in our encoder one is the kind of that is English, and this one is the Hindi. Okay, in our okay, so the output that in our this encoder decoder model, okay, the output that is a Hindi, that is output from the decoder, that can also be a variable length. Okay, that it is not always uh, have the same length of the input sentence. So the output, okay, that output have also variable length. And the third is, that is the biggest challenge. There is no guarantee that if you give an English sentence of let's say 3 words, then it translates to Hindi sentence that will also contain the 3 words. The important point is we are dealing with a variable length, and this is going to be a bigger challenge. So not only in the input but as well as at the output side. And also you have to deal with the fact that if the input has 6 words, then it is possible that the output that may have 60 words. So that can be possible. Okay. Clear? So these three are the main challenges to handle the sequence to sequence kind of data. Okay. So now again the question is why? Why encoder decoder? Why encoder decoder? So the good part is that we have learned a little bit about handling the variable length by studying this LSTM and RNN variable length, that we already that have studied the variable length of input, okay, in LSTM and RNN also. Okay, but that we have to handle it only at the input side, but we have learned only at the input side how to give the variable length of the input only at input side, not in the output. So for this, we have to learn this encoder decoder, this architecture. Because in this RNN LSTM, okay, that the input that has a variable length, that we already that have learned how to provide the input, okay, of a different word length time, step to step in a different time step minute. Okay, so now come to the encoder decoder architecture. encoder decoder architecture. So for this encoder decoder architecture, the prerequisite is RNN and LST. RNN and LST. Okay, so if you know the detail of this RNN and LSTM, then it will be easy for you to understand the architecture of encoder decoder. Okay, so encoder decoder, that this one is the encoder and this one is the decoder, and this encoder and decoder that are connected with a context vector, that already that we have seen this context vector. And here, okay, this input, let me redraw this in the next page. So this one is the encoder and here this one is the decoder. And this encoder and decoder that are connected through this context vector. Okay, and here that is input and this is output. So let's say the input is, let's say input is nice to meet you. Okay, and output is say मिलकर अच्छा लगा. So encoder is basically that section of the architecture where you give your input sentence. Correct? So make sure that you give this input token by token basis. So means word by word basis. We cannot give this as such to this encoder. Okay. So encoder that will try to understand this whole sentence and give an output that will be again a vector. Okay, set of a number. Correct. And here the input that is again that is a kind of vector, and output that is again that is this one is a vector. Okay, and this will call as a context vector. I am talking about this encoder. This encoder. Clear? And context vector, this context vector, that is a summary. This context vector is a summary of the input sentence. Okay, input sentence is nice to meet you. It will create a summary of this sentence. And how was it made? That with the intelligence of the encoder, that we will see how it create this means this encoder output that is in the form of the context vector. Okay, that we will see, and what is going here inside this encoder with the LSTM, that we will see. So this context vector that we will feed, okay, to our decoder, and the job of the decoder is that it will try to understand this context vector. So after understanding this context vector, it will start printing the output on a token by token basis. So inside and this encoder and this decoder, that we will use this LSTM. Okay, so let's say this one is encoder. This is encoder. Okay, so now here one LSTM. The input is nice, and this is what HT, and this is what CT. That CT, that is a hidden state, the previous hidden state. Previous hidden state. Hidden state means that is a short-term memory, and this cell state is that is a long-term memory. Okay, and here this one is again that is H of t. Okay, hidden state. This HT minus M1. This one is HT minus M1, CT minus M1. This one is H of t. Okay, again that is one more LSTM. This one is LSTM. This is LSTM. Okay, so now this is that is again that is H of t. Now the input is 2. This one is the LSTM meet, and this one that is again that is the LSTM that I unfolded this over this encoder. Okay, at different time steps. So nice to meet you. And this one that is again that is H of t and C of t. Okay, so now H of t and C of t that are not same. This one is the now this H of t that is updated this hidden state and cell state. So now we will pass this H of t and C of t to the decoder. Okay, so now decoder is let's say this one is decoder. Okay, so now this H of t, this H of t and C of t here, H of t and C of t. So that is LSTM, 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 and LSTM. So now here this H of t and this C of t. Okay, this H of t and C of t that is in the form of this context vector. This is in the form of context vector. Okay, question is, does number of LSTM units have relation to context window? See, this number of LSTM that here, how many words are there in this sentence? Nice to meet you. There are 4 words. Okay, so now this one is at t is equal to 1, at t is equal to 2, at t is equal to 3, and t is equal to 4. So that we will send the input at different time steps. Okay, means it is not necessary here the number of the words here in the input side, here in the and the decoder, the number of words that are not always same. But here that is one example. So nice to meet you. Here आपसे और आपसे मिलकर अच्छा लगा. So that maybe just you can consider this आप is a different word, say in a different word, or you can consider this आपसे मिलकर अच्छा लगा. So in that way, the 4 LSTM at different time steps, and आपसे मिलकर अच्छा लगा, that in that case you consider the 4 LSTM. In fact, this is a LSTM, LSTM that at different time steps. So there is a one encoder and one LSTM. So just you give the input at different time steps. At t is equal to 1, at t is equal to 1, so nice. At t is equal to 2, then 2, then t is equal to 3, meet, and t is equal to 4, that is you. Okay, and this context vector, this one is the kind of summary of this input sentence. Okay, this one is a summary, that is a context vector, that is a compressed representation, compact representation. This one is a compact representation, and when you will get this compact representation after this last word of this input sequence, when you send the last word of this input sequence, this u, okay, then after this, then it will make a one representation. It will summarize all this nice to meet you. It will make a one summary. Okay, that summary, that is in the form of, obviously, that is a vector. And now this vector, now you will feed this as an input to the decoder. Not only this context vector, but we will send the input also, current input and this context vector. Correct? Then it will provide the output, that is APSE. Clear? Now here the input and output, that is Milker. Now the current input. Okay, these are the HT and CT. HT and CT. Okay, this current and hidden state. Now output, that is Acha. Okay, now here the input. Okay, then output, then Laga. Okay, let's say that is one more, that is LSTM, that is input, and that is output. Okay, so let me just clear. This one is the encoder decoder architecture. Now here, Cauchy's context vector at t is equal to 1, 9. How does it match to Acha in the quarter at third place? Okay, that we will see in this architecture. Okay, when we will feed this nice, this two, this meet, I will explain in detail. Okay, this context vector in the sense of this context vector. Okay, now up to so far is okay. Now there is a one additional this input. Okay, here this HT and CT, that is a context vector. This one is the context vector. Okay, now along with this aapse milkar acha laga. Okay, this is the output. Now this input, that will be the same as the output of this first LSTM. Okay, and here the input of this LSTM. Okay, so let's say this one is at t is equal to 1, at t is equal to 2. So at t is equal to 2, the input along with this HT and CT, that is hidden state. Okay, so along with this, the input is, that is APSE, which is the output of this LSTM. Now the input is, that is Milker. Here the input, that is Acha, and here the input is this. Correct? And now here the input is, that is EOS, and this one is end. Or in place of EOS, that is, you can write it as a start and end. And this start and end is to what is a fixed one in every sentence. So first is input here in the decoder. The input is in the first LSTM at t is equal to 1, that is input is start all the time. Okay, so I hope this architecture is clear to you. So in encoder decoder that we never use RNN because of this exploding and vanishing gradient problem. So we can use GRU, okay, we can use LSTM, but we never use the here encoder decoder inside the RNN. Okay, clear. So now the point is what you do at time step t is equal to 1. Okay, so you provide this input, okay, the input that is a context vector. It is making up say as one word. Okay, okay. See, here I consider this up say, okay, here this up say that I consider here, this one is a one word. Okay, clear? There is no technical meaning is here. So you may consider here a से मिलकर अच्छा लगा. Okay, you can consider here this आपसे. Yes, yes. So now here let us understand this decoder part. So now what you do at this, what you provide at this t is equal to 1 time step. So you provide not only this context vector, this is the context vector. This is the context vector. Okay. So along with this context vector, that you send this spatial symbol. Okay. Spatial signal symbol that you can call as a start. So on seeing this start, the decoder understands that now it has to start producing the output, and it produce a word, and its first time step, the output is upsay. Output is upsay. Now what will happen now at t is equal to 2 time step? The output that come out from time step 1, you will send it as an input here in the second time step along with the internal state, hidden state. And then here you will get the second word, that is Milker. Okay, so you have to keep doing this until you get the special symbol in the output, that is AND. At t is equal to 3 time step, okay, just you feed the input which is the same as t is equal to 2, the output at t is equal to 2. So as soon as the decoder sees that this is the end, okay, it stops producing output. After that it does not run any further more time step, and that is how the decoder works. Okay, clear? This one is the encoder and decoder. So now let's start the training of this architecture. Okay, the training the architecture of this encoder and decoder. Clear? So now I am taking an example of this machine translation. Okay, this machine translation. Machine translation, that is kind of English to Hindi. Okay, so let's say there are two columns. First one is the English and second column, that is the Hindi. Okay, so I'm considering only this two column and two sentence. Okay, two column and two sentence. First column, that is English, second column, that is Hindi, and that we have two sentence. First sentence, let's say first sentence is think about it. Okay, then output is सोच लो. Second, come in, अंदर आ जाओ. So we need to convert into a token, okay, because the input to the encoder is a vector. So token, our this first sentence, think about it, okay. So now think about it, okay, and Hindi, that is सोच लो. And now that is come in here, अंदर आ जाओ. So through one hot encoding, we write the total vocabulary in this first sentence and second sentence. So total vocabulary, that is 5 words. So for thing 10000, about 01000, it 00100, come 00010, and in 00001. Okay, clear? So in Hindi, again there are 5 words. Okay, 2 additional words in Hindi. One is the start, and last one, that is the end. So in total, that is 7 this item. So now start, that is 1000000. Okay. Now search 0100000, and so on. And the end, last one, 0000001. Clear? So now that we have solved the first problem, that we have the numerical input and numerical output. Okay. So now we have to send this input, this data, to our encoder and decoder. This numerical, this data, okay, to our encoder and decoder. So let's start the training process. Okay. Now we will pass the, okay. Now we will pass the row is think about it. Okay. So the first row is think about it. So what will happen just at the beginning of this training is that we will have one LSTM, okay, one LSTM inside the encoder. So this one is the encoder, and there is a one LSTM. This one is a LSTM, okay, and there is a one LSTM inside this decoder. This one is the LSTM, not input. This one is the LSTM. Clear? So now the point is how you provide this vector into this encoder and decoder. Okay, so both of these are two different LSTM, not the same LSTM. This one is the encoder and this one is the decoder. Okay, different LSTM and different weight and bias. Okay, so now at very first, the weight and biases of both the STM, that will be random. Okay, So that can be of any value. So that is the first step. Clear? So now we are sending our English sentence to the encoder. So now English sentence that is encoder, that is first, that is thing. And this one is the HT and this one is the CT. Here that is output, that is HT. Okay, hidden. At time step 1, this input is, that is 10000. Okay, and the output will come out here, and this one is the hidden state that will propagate, further from this location, from this side. Then at the next time step, so now this is the thing. Okay, at t is equal to 1, now about at t is equal to 2. Okay, now 0 1 0 0 0. Then at time step 3, okay, then 0 0 1 0 0. So now in all three time steps, okay, in time step 1, in time step 2, in time step 3, our encoder is, this encoder is trying to understand this data, and along the way it is updating the hidden state also. Okay, so as soon as the last time step, that is t is equal to 3, this is important. So as soon as the last time step, that is this t is equal to 3, that came. Okay, so now from here the final ct and ht, that will be that as an output as a context vector. This one is a context vector, and whatever values are in the ht and ct, they will go and feed into the decoder. Correct? Clear? Now the decoder. So as you know, the decoder is also an LSTM. Here, the decoder that is also, that is LSTM. This one. Okay, and this LSTM has two input. First is the context vector. This one is the context vector. Context vector, that is HT and CT from the previous HT and CT, and at the same time, okay, and at the same time, we also start inputting our Hindi sentence. So first of all, we will send start, which has a one hot encoding 1000000. Now, what should come in the output of this LSTM at t is equal to 1 time step, that's t is equal to 1 time step. The output should come, the first word, the output that should come, that is first word, is Soch. Obviously, this is neural network architecture, and it cannot print this Hindi, this Soch. So what can it print? It can print number. So number, or you can say the set of number, which you call as a vector. Okay. So the one hot encoding corresponding to Soch, this one is 0 1 0 0 0 0. One hot. So now it will produce this 0 1 0 0 0 0 and one hot encoding for this correspond to Soch. Okay, so we have to output this vector. So there I will that explain to you what exactly happened here, this output. How do we get this 0 1 0 0 0 0? Okay, how do we get this source? So now this is easy. Now we are just feeding this at t equal to 1 time step the input start, and this one that is second input, that is along with this current input. This one is the current input, and this one is the context vector, that is the previous hidden state. Okay, so now let me explain in detail. See, this one is here. Let me just explain this here. Uh, this source. Okay, so now here there is a softmax layer. Softmax. So there are nodes in this softmax layer. Okay, so there are nodes in the this softmax layer. So how many nodes are there? Exactly as many nodes are there in the vocabulary. So how many items are there in this output? That is 7. So the 7 number of nodes that will be there. Okay, so the number of nodes that will be 7. So for every word that we will take 1 unit. So now see this one. Okay, and here this one is the output of the LSTM. This one is the output of LSTM. Okay, so this one is a start, this one is a source, this one is low, this one is under, this one is this one is Jao, this one is N. Okay, so now what is the use of this softmax? That it will generate a probability at each of its node. So it will generate a probability. So the probability, that is a y cap. So that is, let's say, 0.20 0.0 0.1 0.1 150. Okay. So yes. So in this encoder and decoder, so that have the encoder is different than the decoder. Inside this encoder and decoder, there are different LSTM. So the word length that may be different. So here in the word length in this encoder, that English sentence that may differ the word length of this output language. Okay. So here, let's say for example, here the input, this input language, let's say input language is French, let's say for example. Okay, and in this one the sentence that has a, let's say, 5 word. Okay, this one is a 5 word, and output, let's say it's a 15, may be possible. Okay, so this one is a, let's say this one is a French, and this one, let's say, that is a English. Okay, let's say this one is a 15 words. in a sentence, and here that is a 5 words. So along with this 15 word in this English output language, so the two additional word, that first one is a start and last one that is a end. So in total that is a 17 word. Here that is in total that is a 5 word, or vice versa, maybe sometimes in a French, this input language, the number of word in a sentence, let's say 5, and let's say in output language, that is the English, number of word in a sentence, let may be less than 5. So encoder will translate to word in a decoder. So one word, this encoder. So here encoder, here is a one word. This one is a at t is equal to one thing, at t is equal to 2 about, and t is equal to 3, that is it. Okay, and here this sorry, yes, here. So at t is equal to 1, the input is start, or output is, that is single, that is Hindi word, that is absent. So now I did not understand this two word in a decoder. So one word in an encoder, that is translate like a one word that is at the out decoder. So let me explain this complete this encoder and decoder architecture. Okay, maybe at the last your doubt that may be clear. Okay. So now point is okay. Huh. So now this one is a high cap. This one high cap. Okay. So the output that will be, so the output that is output that are having the probability. Okay, so since this one is having the highest probability, that is 0.3, so output that will be, so output will be 0 0 0 1 0 0 0. So our output that will be this one, means under, according to the one hot encoding 0 0 0 1 0 0 0. So this is how the decoder output a particular body. Okay, so the output that should be Soch. Okay, but here the output of this LSTM at t is equal to 1, the output that is this actual output, this one Soch, but predicted output that is under. Let me explain one more time. This one is the number of these nodes. So number of nodes in a softmax equal to the number of this total vocabulary in the Hindi, this output language. So in the output language, the total this vocabulary, that is including the start and end, that is total in 7. Okay, clear? So now this, it will generate this softmax at every node, that is a probability. So now let's say this one is the probability, that is y cap. So what will be our output? The output that will be the term whose probability is highest. Okay. So here the since the probability of this 0.3, the probability of under is highest. So our output that will be 0 0 0 1 0 0 means under. Now what is the problem? If you can recall this one, the architecture, then here. Okay, so what we have to do, whatever the output that comes in first time step, you have to send the same as input in next time step. This one. But here the output is different than this source. Okay, that is under actual one. The problem is that you should have sent source to the next this LSTM, okay, at t is equal to 2, and corresponding to this one mode encoding that source is 0 1 5 times 0, but since here this is the output, okay, this one is the output, this one is the output, so you will have to send this 000 1 000. Okay, so now here you have to remove this source and you have to send this one. So in place of this 0 0 0 1 0 0 0. Okay, but what will happen? Okay, after this, so the training that will become a little slow. So the researcher has decided that even if there is some mistake at the output during the process, the output is correct, but input at the next time step, that is one. And this we call as a teacher forcing. Although the output is wrong here, okay, 0 0 0 1 0 0, but we will send the correct input at t is equal to 2 time step. So here at t is equal to 1, so the input is that is start, okay, and output, that is, let's say this one is a wrong output, okay, but we will send at t is equal to 2 time step the correct input. Okay, let's say again that is a wrong output. Let's say, okay, this one is the hidden state, okay, this one is the context vector, and at t is equal to 3, this one, let's say, wrong output. Now again that we will send the correct input. Here that is the wrong output. Okay, so you are having a doubt in your mind that why is it making so many wrong predictions? This here that is a wrong output. Here that is, let's say, that is a wrong output. Okay, but here that we will send the correct input. So the question is, that is why it is making so many wrong predictions. Then it is a simple thing that you have just started training. There are random weights. Okay, so it is just giving any output. So whatever is in the vocabulary, it is considered random. So now after t is equal to 2, so we will move to the next time step. Let's say at t is equal to 3. Okay, so let's say at t is equal to 3. Now see this one, at t is equal to 3. Okay, so now we will move to this here at t is equal to 3, and in the next time this at t is equal to 2, the next time step. So now we will this send the this hidden state. from the previous LSTM, and again this, after sending this HT and CD, we will send this low. Okay, here that is start, here that is a source, here that is low at t is equal to 3, at t is equal to 2, at t is equal to 1. Okay, and again that we will do the processing inside this LSTM. Okay, there are two input HT and CT, and the current input that is low, and then output that will come out. Okay, and the output that will be this after this softmax. Okay, and we will get an output vector. Now let us assume here this is the softmax, here this is a softmax, here also that is a softmax. T is equal to 3 here. The output, let's say that is a y cap is equal to 0 0.1, 0 0.2, 0 0.2, 0 0.1, 0 0.3, 0 0.1, 0 0.4, let's say this one. So now if you focus, then the probability of last one is high. The probability of last one that is high. Okay, and this correspond to end, which means that the prediction of our model at t is equal to 3, the third time step, that is end. 0 0 0 0 0 0 1. Okay. So if I ask you what is the correct time step according to this time step, then I guess you will be able to tell that since the sentence is ending, so has out at this time step. Okay, then when you stop here, you do not go further in the time step. Okay, so now you have to just stop, and that is the correct one, that is the end. Okay, so this is all about the training. This is all about the training. So now next that we will calculate the loss. Okay, so now how do you calculate the loss? So y is 0 1 0 0 0 0 0. Okay, that is a source. Now 0 0 1 0 0 0 0. This one is a low. Okay, and 0 0 0 0 0 0 1. This one is the end. And y cap, let's say for example, okay, for example this one is a 0.2. Okay, let's say 0. Again 2, 0.3. Okay, and 0.1 and so on. Okay, and here this y cap is 0.1. Okay, 0.3, and so on, let's say, and here that is 0.1, 0.2, and so on, that is up to, let's say, 0.4. So now this one is at t is equal to 1, this is at t is equal to 2, and this one is at t is equal to 3. Okay, so now, so first you have to decide which loss function you have to use. So we have to pick one category, okay, out of 7 categories. So at t is equal to 1, at t is equal to 2, again you have to pick one category out of 7 category, and you have to pick one category out of this 7 category at t is equal to 3 times 10. Okay, so this is the multi-class classification problem. This one is a multi-class classification. So this one is a multi-class classification. So now the loss function, that is categorical cross entropy. So categorical cross entropy. So now loss function, that is yi log of this yi cap I is equal to 1 to 7. So now loss at t is equal to 1. Okay, that is corresponding that bitwise just multiplication. So minus में 1, okay, multiply by, now you see this one is the yi, okay, and this one is the y cap. So now 0.2 multiply by 0, 0.2 multiply by 1, okay, and 0.3 multiply by like this one. Clear? So let's say, for example, let's say this one is a 1, okay, and yes, let's say this one is a 1. For example, this one is a 0.1. So now minus of yi minus of 1 log of 0.1. So log of 0.1, that is minus of 1. So minus of 1 multiplied by minus of 1, that is equal to 1. So now loss at t is equal to 2, again that is minus of 1 multiplied by log of 0.1. Okay, again that is equal to 1. And loss at t is equal to 3. So now you see the 0.4, that is the highest probability, and corresponding to this bit, that is equal to 1. So now you see minus 1 multiplied by log of 0.4. Okay, now just you calculate. Okay, maybe let's say for example, that is coming, that is equal to 0.5. Let's say for example. So at t is equal to 1, at t is equal to 2, our model that has done a mistake, but at t is equal to 3, now see this one. This one is the correct one. At t is equal to 3, the model had given the correct output. So when it gave the correct output, okay, the loss is less, and when it gave the wrong output, the loss is more. So now you calculate the total loss, that is total, that is loss, that is equal to 2.5. Okay, or you can the average loss around 0.8. Clear? So let us assume that we have taken this total loss. Okay, so total loss, that is a 2.5, and we have done the forward propagation. Okay, and we have calculated this loss. Now the back propagation. Okay, so now we will do the back propagation. Back propagation. Okay, so let's finish this back propagation. Okay, then we will wind up this session. So for this back propagation, there are two things required. First is the gradient calculation. First one is the gradient calculation, and second is just to update the parameter. Just to update the parameter. So that is back propagation. That is done by, that is two things. Okay. So now I will tell you about this gradient calculation and this second one, that is a update parameter. So let's talk about this first, that is a gradient calculation. Okay. So you calculate the gradient of the loss with each of the trainable parameter. With each of the trainable parameter. Okay. So that is all the parameter that is in LSTM, all the parameter that is in dense layer. Okay. All the parameter in this softmax. So you have to calculate the gradient of the loss. Okay, with respect to the trainable parameter. And after that, what you do is that on the basis of this gradient calculation, okay, the gradient means, the gradient meaning is, so this gradient meaning is basically how much a particular parameter that has contributed to the loss function, and that parameter in which direction should be adjust so that the loss can be reduced. So this is the advantage of this calculation of this gradient. And as soon as you have calculated the gradient of this gradient calculation, so what you have to do now, you have to update the weight that is on the basis of the gradient, this gradient. Okay, clear? And that is this gradient calculation, that is through this stochastic gradient descent or any other optimizer like ADAM. And this adjustment of this parameter, that is done on the basis of this learning rate. And the learning rate is basically a hyperparameter which decide at what speed we are increasing or decreasing the gradient. Clear? So summary is, so first of all that you have applied the forward propagation. Okay. So forward propagation on the data with initial rate. Okay. So by doing so, you will got some output. Okay. You compared that output with our correct, uh, this one is a y cap. Now just you have to compare this with our true output, which gave the loss. On getting the loss, we calculated the gradient with respect to the each of the trainable parameter. Then gradient. Okay. The trainable parameter, that is LSTM, dense layer, that is softmax. This gradient is then used to update the weight. Okay, using some optimizer, let's say ADAM, and to decide at what speed this update should happen, you have the learning rate, that is eta, and from this we got our new weight. And once you get your new weight, now you can repeat this step again. Okay, where you will take a new training example. Okay, now we had two training example. One was thinking about it and second was come in. Now you will grab the second one, second sentence. You will send the second sentence to this encoder decoder where the weights are now updated according to the old error. Okay, so you will do the forward propagation. Okay, then you will get an output compared to the actual one. Then you calculate the loss. Okay, then gradient, then update the weight, then through this learning rate. Okay, then you will get the new weight. Okay, correct? Okay, so that is all about the this encoder and decoder. So now the question is, how does it differentiate between wrong and correct? Okay, so now the last one is the prediction. The last one is, that is a prediction. So let me explain this, the prediction part also. Okay, so that it will be clear to the complete encoder and decoder part. So now the last one is, that is a prediction. So now suppose now we are giving a new sentence. Okay, so first of all that we will tokenize the sentence. Okay, then send it to the this encoder. on a word by word basis. So let's say this one is the LSTM. This is a vector, okay, through this one hot encoding. This one is a HT and this one is a CT and this one is the output. Okay, this one is again that is HT. This is again that is a vector. Okay, so now finally we got our CT and HT in the format of this context vector. Okay, and now the work of the encoder that is done. This is the only the encoder part. From here, now the work of the decoder that will start. The only difference is now we don't know the true value. We don't know the in advance what the correct translation is. Okay, so now this one is a, let's say this one is a decoder. So now input is that is start. Okay, and this one is HT and this one is a CT. And through this one hot encoding, that we will just provide this as a in a vector. Okay, this start. Let's say this 10000 according to the this vocabulary. Okay, so first of all that we will start this along with this context vector, the input. Okay, clear? So the basis of on the basis of these two input, okay, uh, the decoder that which which was trained will give an output. This decoder that is already trained, okay, on the two input. First one that is a think about it, and second one that is a coming. So this decoder that is already trained, so that it will give an output and send it to the softmax layer to calculate the probability. And let's assume for a moment that the probability is something that is, let's say 0.1, 0.3, let's say so on. Okay, so I told you we have to print the word whose associated probability that is highest. So you can see this, let's say this second probability that is high. So now we will see which word is at second number. So now that is second number, that is Soch. So automatically our output that will come here. So now what will happen? Now the next thing is a little different point. What we used to do, we used to find out at the time of training what should have been the correct output. In this next stage, we used to send the correct output. Okay, here at t is equal to 2, that we call as a teacher forcing. Every time we have to feed the correct input, whatever be the output at the time of the training, but we don't have the correct level here is prediction time. So what we will do, whatever the output has come here, we will send it the same one. So we will send the Soch, that is one hot encoding. Again, there will be a calculation. According to the weight, the output will come. The output will go to the softmax. Again, the probability. Okay, and the output that we will send again, the same output that we will send again to this at t is equal to 3 time step, that is input, and so on. So that is the prediction. So according to this one, the output that maybe okay. Soch Jao low this end. So in prediction, what if the input is an unseen sentence? Yes. So this input that is an unseen sentence. Okay. So let's say this sentence is let's say I want to play cricket. This one is an unseen sentence. Okay. So unseen sentence. So the first at t is equal to t1 time step. Okay. Now ht and ct at t is equal to 2, then we will feed this 1. At t is equal to 3, that we will feed 2, and like this one. So here in the prediction, teacher forcing, that would not be there. The teacher forcing, that always, that at the time of the training, teacher forcing means so this one is the LSTM, that is output, that is, sorry, decoder. So here let's say that is a wrong output. Okay, so here the input, that we should send the same here input. This one at let's say this one is a t is equal to 1 time step, and this one is a t is equal to 2 time step. So at t is equal to 2 time step, the input that would be the same as the output of this t is equal to 1 time step. But here, as this output is a wrong output, so now we will feed the correct input here. That is a teacher forcing. That is at the time of training. But we will not do this teacher forcing at the time of the prediction. Okay. So now this is all about the encoder decoder. Okay. In the next, maybe in another day, that we will discuss the attention mechanism and transformer. Okay, so both the transfer mechanism, sorry, attention mechanism and the transformer, that we will discuss in some other day in another session. So I hope this encoder decoder is clear to all of you. So if you have any doubt, then please let me know. Hello, is there any doubt? Okay, fine. So now we will wind up the session here. Okay. So next, in the second half, that we will meet at 5 o'clock. So 5 to 7, that is the second session. So thank you all. Thank you for listening to the lecture. Now I wind up the session. Okay. Thank you. Yes. So yes, I want to play cricket. Yes, Priti. So the total number of this vocabulary in this sentence, that is a 5. So correct. Yes. So through tokenization. Okay. So the word by word. So now we have to just convert this each word or text in a vector, in a set of vector, in a form of this. Let's say you can say that is a scalar or a set of vector. Okay. So for the cricket stadium, which is unseen, how again, that is as already that we have seen in the deep learning and machine learning. So first, that is the training data and test data. Okay. So first we have to train our model, and then after training that we will send the this unseen data. Okay, if training of model that is very, if we train the model, that is, if the model is very well trained, then it will provide the output on the unseen data. Okay. Yes, it will come. Okay. Yeah, yeah, it will come. It will come. Okay. Okay. Thank you.